Theorem, unique factorization theorem, UFD. Let R be a Euclidean ring and A be a non-zero element in R. Suppose that A equals to P1, P2, so on, Pm equals to Q1, Q2, so on, Qn, where P's and Q's are the prime elements of R, then M equals to N, and each of P is an associate of some Q, and each Q is an associate of some P. Proof: we have P1 into P2, so on, Pn equals to Q1 into Q2, so on, into Qn. Now P1 is a divisor of P1, P2, so on, Pn. So P1 is also a divisor of Q1 into Q2 and so on, Qn into Qn. Then by corollary, if P is a prime element in a Euclidean ring R and P divides the product A1 into A2 and so on into An of element in R, then P divides at least one of A1, A2 and so on An. So P1 must divides at least one of the Q1, Q2, so on Qn. Since R is a commutative ring, therefore without any loss of generality, we may suppose that P1 divides Q1, but P1 and Q1 are both prime elements in R. So P1 and Q1 must be associates. That is, we have Q1 equals to U P1, where U is a unit in R. Thus we have P1 into P2 and so on into Pn equals to U P1 into Q2 into Q3 and so on Qn. Cancelling 0 not equal to P1 from the both sides, we get P2 into P3 and so on into Pm equals to U Q2 into Q3 and so on into Qn, equation 1. Repeating the above argument on the relation equation 1 with P2, if n is greater than m, then after m steps the left hand side becomes 1, whereas the right hand side reduces to the product of some units in R and certain number of Q's, but the Q's are the prime elements of R and so they are not unit in R. So the product of sum of the units in R and certain number of Q's cannot be equal to the 1. So n cannot be greater than m. Thus n is less than equal to m. Similarly, interchanging the role of the p's and q's, we get m is less than equal to n, hence m equals to n. Thus we have shown that p is an associate of sum of q, and conversely every q is an associate of some p. Hence the proof of the theorem.